space. So this will be a second lecture, or half a lecture. It's going to be short, with more words than equations. Then we'll plunge into mathematics immediately after. But this is important, and don't underestimate this, because I think a lot of the confusion in quantum gravity is that people are confused about the notion of space and time, both of them. And to do quantum gravity, we need to rethink space and time, and this has to be done clearly and cleanly. Otherwise, one is confused forever. So I'm going to talk about space now. I'm not going to talk about time, because in the presentation of the theory, it's easier to talk about space first and time later. Now you're going to say, well, wait a minute, what about Einstein space-time? Yeah, we'll bring order into that, but let's do one step at a time. There is I've written repeatedly about that, but my way of thinking about this has evolved. So it's cleaned up, not really changed, but being cleaned up, especially the way of saying things. So I'm going to follow now a recent paper that I put on the archive last year, because I was asked by some review thing to write about space and time in loop quantum gravity. So there is a paper whose title is Space and Time in Loop Quantum Gravity, which is on the archive, has been on the archive for a few months. It is in the Dropbox, just in case you want to take a look at it. I will not cover everything in that paper, but some of the ideas are mentioned there. So the key point which raises confusion is that when we say space, we mean different things. That's the key point. And if we disentangle one from the other, we get clarity. If we keep just calling space everything together, we get confusion. And the first thing we mean when we say space, let me call it a relational space. It will be clear in a moment what this means. For the moment, it's just a word, relational space. It's the following thing. We talk about space when we talk about where, right? Space is the thing we talk about when we talk about where. And if you think what how we use where, how do we use where? Where are we? We are in Marseille. Where was I last week? I was in Rome, in my house, or next to the chair. Or I'm in the Sahara. My friend, my girlfriend is in London, okay? So what am I doing? I am talking about the proximity of an object with respect to another object or a set of objects. Right? I'm in Rome, imagine I'm next to the Colosseum, or the Sahara, you imagine all sand around. In London, this London Tower, the Tam, and so on. So we always answer to the question where by saying next to what something is. This discussion, which I just gave you, is not new. Of course, it's old. It's in Aristotle, and it's beautiful. Aristotle discussion of the notion of location. Aristotle is very careful, of course, being Aristotle. He defines location as the inner boundary of the thing surrounding a thing. So my location is the air here around me, and the location of the air is the building, location, and so on and so forth. So the idea here is that space is a relation between things. And Aristotle has discussed this in great detail. Another who gives a very clean discussion of the same idea is Descartes. Descartes gives a name to this relation, which is contiguity. Okay? The inner boundary of the things surrounding a thing of Aristotle means they touch one another, they're contiguous to one another, they're next to one another. This nextness is what we call about space. Who is related to whom? So the image here is that you have things, you have another thing, 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 and they are not scattered. This as a special relation with this ones, which has not with this one, because this is next to this is not next to this because there are things in between. This being in touch with one another, it's a property of the world. In the world there exists this relation, and this relation is space. Okay, and that's what we mean when we talk about where. We locate us with respect to other things. There are two corollaries of that. 1 and 2, which were very clear to all these people and many other people who talked about space in this manner, but these are particularly clear writers about all that, and particularly deep and precise writers. One is that if you think space in this way, if you get clarity about space in this way, there is no empty space. There is no vacuum, because if you take away all the things, there is no space, because space is a relation between things. Right? If you take away the man and the woman, or the man and the man, there's no marriage. Or the woman and the woman, there's no marriage. It's just a relation. Marriage is a relation between two people. If you take away the people, it's not something remains there. It's nothing. Which seems in contradiction with some more modern way of thinking, and I'll say in a moment why we see a contradiction. The other thing is that motion is, so what is motion? Motion is change of location. Location is change of what is next to me. So I'm moving because I'm next to you, and now I'm next to you. This is motion. So motion, in fact, that's Descartes' definition of motion. An object A moves if it is contiguous to B first, and then it becomes not anymore contiguous to B but contiguous to C. So there's a change of contiguity with respect to other objects. So motion is in quote relative to other objects, is a change of who is next to who. That's what motion is, relative to other object. This set of relation of continuous change, because this one is shifted and it goes next to this one. All right, this is a very clear understanding of what space is. You immediately realize that it's not what you read in physics textbooks. It's completely different than what you read in physics textbooks. So in physics textbooks, what you're told at school is that space is something else. So there's another notion of space. And this other notion of space, quite remarkably, is not ancient, is modern, and it was introduced by Newton, what we call Newtonian space. In fact, it was introduced by Newton explicitly disputing, in a certain sense, Descartes, especially, and saying, in the Principia or in other texts by Newton, saying with this notion of space we don't go ahead and do decent physics. In fact, if you write the physics of Descartes, it's completely clear the discussion of space, but then the physics is, Descartes physics doesn't work. I mean, it's contradictory, it's ugly. There's beautiful things, but there's just and Newton puts order into it. Of course, it has Kepler result, it has Galileo result, it has mathematics, it's Newton. And so he introduces another notion of space. which I'm going to describe in a moment. But what I want to emphasize, which is something you do not find usually in books in this discussion, is that Newton does not say at all in the Principia that that's a wrong way of viewing space. Newton says there are two notions of space, separate, different. One, so is a distinction he makes. And he calls, he calls vulgar, popular, all sort of bad names, common, let's skip common. And the other he calls true or absolute. Let's keep true. And the common notion of space is Aristotle Descartes space. So he's not saying, this is important, it's enormously important for quantum gravity. Newton is not saying Descartes and Aristotle are wrong. He's saying, besides Descartes and Aristotle notion of space, there's another one, which is the true one. So what's the true one? Well, space is an entity. It's not a relation. So space is there even if there are no things. Forget the things, take away the things, there remains something, which is space. And is an entity with a structure, and in fact a geometrical structure, which he describes in details, and I'm not using his own description, I'm using modern description, which you all know very well. It's a three-dimensional space, sometimes it's called E3, which is a three-dimensional vector space. Let's call it R3, with a notion of distance. So it's a metric space, and in fact it's a metric space of what we call today Euclidean geometry. So it's a table. Okay, it's a table, or let me give you a. It's a container of the world. It's a container of the world, and in this space things move. The object moves, and between two objects in general there is empty space. And to move is not to move things with respect to one another, is to move with respect to space. Okay? So Newton is postulating an entity which somehow was not seen or considered or whatever up to now, and says if we postulate this entity we can do physics. Okay? He postulates the space, and of course he postulates time also is another entity. The discussion about time is going to be very parallel, so there's also some time r, and a particle or an object is described by its position, so where it is in this space, as a function of time. So his main equation, which is of course you all know, d square x over dt square m equal f. This position and this time are with respect to the space. Now, brief parenthesis. A lot of this has raised all sorts of confusions. Of course, he's not disputing Galilean relativity. He's not saying what I want to say is that you hear often that Newton was wrong with absolute space because of Galilean relativity. That's not the discussion here. What's absolute here is the acceleration. So the geometrical structure of space allows to distinguish a straight motion from a curved motion, or from an accelerated motion, and that's absolute. So acceleration for Newton is acceleration with respect to space, not with respect to other things. And he has this bucket experiment. I don't know if you've ever viewed the bucket experiment, which is an extraordinarily subtle and smart piece of sort of ideal experiment. He says I did it for real. Do you all know the bucket experiment? Who doesn't? You're only 1, 2, 3, 4, 5, 6. Oh, many people don't. So okay, so let me give you very, very rapidly what it is. You hang the ceiling a rope, and you have a bucket, un secchio, full of water, hanging on it. And then you turn the rope many times, okay, and put it still, and then you let it go and you look. And then there are two phases. The point is that there are two phases. One is that because the rope is all thwarted, the saw starts turning and turn, but at first you notice that the water does not turn. Okay? So at first the water is still, with respect to you, the water is still fixed and the saw turn. Then slowly what happens is that the water starts turning by friction, so the saw and the water turn together. Okay, that's what these two phases. And the observation is that in the first phase, the surface of the water is flat. In the second, the surface of the water it's concave. Okay, that's two observations. And now here's the reasoning. He says the concavity of the water is an effect of rotation, no doubt about that. But with respect to its immediate surrounding, which is the saw, the bucket, in the first phase, the water is rotating with respect to its surrounding. In the second is not. So, if motion, like Descartes want, is by definition motion with respect to its surrounding, the water, according to the Descartes definition of motion, is not rotating in the second case and is rotating in the first case. It's not rotating when the bucket and the water goes together, and is rotating when they're moving with respect to one another. So, according to the Descartes definition, there is no motion of the water in the first phase, but there is in the second. But the effect is in the second, not in the first. Therefore, motion that has an effect is not motion with respect to the surrounding. It is motion with respect to something else. To what? To absolute space. That's proof of the existence of absolute space. In modern terms, there are inertial forces. That's an inertial force. So if you sit on the bucket, you see the water going like that. Is an inertial force. Inertial forces prove the existence of absolute space. Careful that Newton says openly and clearly, this is what you see. This you don't see, you don't perceive, you have to use mathematics to detect it. You have to use subtle observation to detect it. So for Newton, the space container is not something we have access to. We have only access to relative space. The space container is something you reconstruct by subtle use of physics, mathematics, from the motions. So the common motions, you also use apparent. From the notion of space, which is the common, the apparent, from the notion of motion, the common notion of motion is Descartes, is relative motion. That's the apparent one, but behind that, as a physicist, I can reconstruct the existence of some entity, which is the space, the absolute space, that defines acceleration. And in terms of that, I can write my physics. So that was Newton, and the reaction of most intellectuals at the time was, come on, you're messing up everything. This is so clear, why do you need that? Okay? Leibniz is a typical reaction like that. There's a famous Newton-Leibniz debate, more precisely Leibniz-Clark. Clark was a follower of Newton debate with some letters that philosophers often study today, in which is sort of presented that Leibniz has strange relational ideas. Leibniz was just defending the traditional way of thinking space against this novelty. Now this novelty of course works so well engineering today build airplanes and houses using this logic. So we all got used to the idea that there is this background space on which things move. But that's an idea by Newton. Good. So then, of course, comes two more steps. One is super simple, and the other one is the key one, and I need a third blackboard, which I don't have. So I'll kill a little bit of Aristotle. And I'll do it here, which is Einstein. And it's two steps, one very small, so I put it here in 1905 with special relativity, in which, of course, there is some understanding about space and time getting together, but this does not change. So special relativity is still completely in this logic. The only difference is that instead of having this object here, which is space, so instead of having E3 and time R, we go to Minkowski space, four-dimensional Minkowski space. But it's still this.
It's 1905.
Yeah, thank you. Thank you very much. The change with respect to the notion of space and time is, of course, 1915. Now it's really 1915 with general relativity, which is a discovery of what? General relativity is a discovery. And what is a discovery? The discovery is that this entity that Newton has added to the tradition of understanding of space and time, it's there. Newton was right. There is this entity, but is not a fixed non-dynamical entity, is nothing else than the gravitational field. So this is Einstein, 1915. So it's a third change, so 3. It's called general relativistic in quote space-time, is a discovery that Newtonian space is indeed an entity, but is a dynamical entity. In fact, a field very much like the electromagnetic field, E and B. In fact, Einstein's model for general relativity is Maxwell theory, so he has his, Einstein was very much impressed by this idea of the electric and magnetic field. It was completely clear that the idea was good. Maxwell attempt to derive the field from mechanical was completely abandoned. Maxwell theory was wondered fantastically. There was all the technology. The father of Einstein was building power plants in northern Italy with using Maxwell equations. So little Einstein was very impressed by this magnetic and electric field that actually moved engines and so on. So it was under the spell of Maxwell. And Faraday, the field is all over, it's an entity, it's a stuff, okay? And he realizes that this thing that Newton has added, it's not so strange, like Leibniz wanted after all, it's just a field. Well, of course, Leibniz didn't know about fields, nor Newton, but at the end of the 19th century, beginning of the 20th century, people knew about fields. Good. So it's a field. So this field here is what is in quantum gravity, what is going to be the quantum gravitational field. It will have quantum properties. It will be granular. It will be in quantum superposition. It will interact, will be in measurements and interactions and projections or wave function or whatever. It will have all the quantum properties that you want. Okay? So if by space you mean Newtonian space, it's going to completely disappear in quantum gravity, because this continuous container, this table on which, this canvas on which the world happens, it has become dynamical and has become quantum. So very little of the properties of Newtonian space remain, because it's not fixed, it's not continuous, it's not E3, it doesn't have this shape. It's a quanta of gravity interacting. So it's completely lost. Clear? But the old relational notion of space has never changed. There are things can be related with respect to one another. I can say when two things are contiguous. We can say where. We can say that this thing is next to this other thing, and so on, like in the traditional way of viewing space, which Newton never dared think contradicting. He was just adding a new structure, and in fact a difficult to see structure, because what we interact usually with in our daily life, it's a relative notion, it's this relational notion of space, not Newtonian space. So, question, do we expect in quantum gravity space to remain there? Well, depends what we mean by space. If we mean the common notion of space, where are things, how are they next to one another, yes, everything is going to remain there. There is a notion, there should be a notion of contiguity, there should be a notion of where. If we expect anything like that to remain there, no. Because the Newtonian background space has been unmasked to be nothing else than a field, and the fields we know have quantum property, so it's going to be granular and probabilistic and so on and so forth. Is that clear? Two more comments to close this story.
So GR is based on the absolute idea of space, right? So is it possible to derive GR with the space-time as a field starting from the other notion of space?
No. No, because the other notion of space doesn't know the existence of the gravitational field, doesn't know the existence of this special object. You can view it the other way around. I mean, space is say who is next to who. Okay. There happen to be one of the objects of the world which is a gravitational field, quanta of gravity. In the classical limit, this is a field. It's the g mu nu of Einstein, g mu nu of x of Einstein. In our experience, it's very, very close to the Minkowski metric. It's convenient to use this as a reference with respect to which to locate ourselves. So we can locate it using distances, using rods. But a rod, what is a rod? A rod is something that keeps its length when I move it around, the length being the square root of g mu nu, dx mu dx nu. So a rod is a measurer of the gravitational field. that what it is? It's a set of atoms that interact with the gravitational field in a way that keeps a certain amount of gravitational field. So we use the gravitational field as the location, like we use the Earth for locating us as long as we move on the Earth. When we have a map on the Earth, we use Marseille, the Mont Blanc, Genève. We use this object so we use this object to locate ourselves, which is perfectly fine. But it's not that this object by itself has necessarily a special status with respect to the other objects of the world, like the electromagnetic field, the Dirac field, the Young-Mills fields, or the others. So in other words, if you want to do quantum gravity, you have to go back to a weaker notion of space, which is the relational space of Aristotle and Descartes, and interpret GR not as the discovery that the gravitational field is space-time, but the other way around, as the discovery that space-time is nothing else, Newtonian space-time is nothing else than the gravitational field.
How do you reinterpret the bucket experiment?
Very good. Very good. So in the bucket experiment, what is in play is not just the water in the bucket. It's the water, the bucket, and the local gravitational field around. The local gravitational field is g mu nu, the value of g mu nu around. So the water, put it this way, so there's an effect, because the water is rotating, of course not with respect to the bucket, as Newton proved, but with respect to the local gravitational field. And in fact, if you do the bucket experiment with the North Pole, and you do it very, very precisely, the water, put it like that, not when it rotates with respect to the fixed stars, but when it rotates to the local gravitational field, which is dragged by the Earth, is one of the effects of gravity, right? The Earth rotates, and the gravitational field just above it, there's a little magnetic effect, such that the inertial frame is slowly rotating. So there's a field there, and the water is flat when it's not rotating with respect to the field there. So in a sense, you can rethink the bucket in purely Cartesian terms, as the water moving or not moving with respect to something there, which is the gravitational field, the local gravitational field. It's purely local phenomenon of something that moves with respect to something else.
Sorry, I don't understand. At the North Pole, what should we see?
That the water is concave, so there are inertial forces. When it rotates with respect to what? Not the stars, because of the frame dragging effect of general relativity, but with respect to the local gravitational field. So the local gravitational field determines the inertial frame, which is slowly rotating with respect to the stars. So the effect is due to the rotation of the water with respect to the local value of gravity.
So space, it's a matter of topology in some mathematical sense.
Yeah.
What is near to me?
Yeah.
And Newton and Einstein provided a geometrical structure from which derived the notion to be close to someone else, if I well understand. And another important thing in the motion, maybe the definition of an inertial class of reference system, as you said now, no?
That's right.
So
which follows from the metric.
Follow the gravity is inertial. What is disentangled? The motion, the acceleration disentangled from the gravity are not inertial.
That's correct.
You can say that this is an assignation of space, so an assignation of a topology, and eventually a geometry from which derive the topology, and an assignation of inertial system.
Yeah, the inertial system follows from the metric structure. It goes together.
Even the matrix you have also, right. But if you have a more general structure,
right,
as in the granular space.
Right, but the point is that to talk about space, you don't need to talk about distances and inertial frames. at this level, and you still have a notion of space. That notion of space remains in quantum gravity.
Okay.
The rest is interaction with the gravitational field.
So you don't have in quantum version of gravity any notion of inertial frame?
No, you can talk about how things interact with the gravitational field. You had a question? Okay, I was hoping already to go into math, but I will do this after. So we have 5 minutes left, so just let me say one little thing to sort of close up this space conversation. It always struck me, this is Aristotle's intuition of what we're talking about when we're talking space. This is Newton's intuition of what we're talking about when we talk space. Here there's no vacuum, no empty space, by definition, because here there is. Okay? So there are sort of two intuitions about how to think the world. In fact, Newton did not invent this from nothing. He says explicitly that he got it from antiquity, from this tradition of ancient science, which is not the Aristotelian one, was the atomistic one, from Democritus. So Democritus has this picture of the world which is empty space, vacuum, with atoms moving. And Newton knew it and says explicitly that his picture of the world is grounded in that one. Of course, much more precise, mathematical and so on, predictive, but it's Democritus' intuition. So this idea, empty space with little things that move around, atoms, in Democritus' language, is also sort of ancient. And Aristotle criticized it very, very strongly. He says, no, you cannot do that. It doesn't make any sense. And the critic is exactly, what is this vacuum? If you have two things, says Aristotle, if there's nothing in between, there's nothing in between. So how can there be nothing in between and something in between? Either is something or it's nothing. And in fact, if you read Democritus, you cannot read Democritus because we don't have Democritus text. But if you read the fragments around, it's tremendously confusing what Democritus says about empty space, because it says it's non-being. There's the being, which are the atoms, and the non-beings, which are the vacuum. So the vacuum is halfway between being and non-being. It's a non-being which actually is. It's horrendous. It doesn't make any sense. Now, the comment I wanted to make is the following. Where do these two intuitions come from in our experience? If you think for a moment. They come from a very peculiar, accidental feature of the actual environment where we happen to live on this planet, in this particular, on the surface of this planet, which is what? The air. Question, between me and you, is there something or not? You can answer both. And they're both right in their own way. You can say, of course there is something, there's air. Right? We live immersed in air, so we live in a full. But the air is so thin, this is just an accidental fact of the way we it's so thin that we think as if it was, we can think as if it was not there. In fact, we usually talk as if it was not there. We say, between me and you there is nothing. What is in this room? There are some chairs, some tables, some people, and that's it. We don't talk about the air. So if you want, Aristotle, it's very Aristotle, right? It's the first of the class. It's very precise. It says, of course, there is something between me and you. There is air. Okay? So everything is full. There's no way of taking air away. Okay? So it's just reflecting. It has been precise about the structure of the world. The world is full. And it's right in a sense, right? You know, Torricelli had this experiment which takes the air away, but we know that even if you take the air away, there's all sort of stuff remain there, fields and stuff, and electric field, magnetic field, virtual particles, or sort of gravitational field. And Newton in a sense, is much less precise, but he's more effective because who cares about the air? I mean, I want to know how things fall. Okay, he was starting from the experiments and the measurement, the equations of Galileo and Kepler. So forget the air, simplify, make a model, and so he invented this thing here, which is empty space, which was previously considered, which does not come from nothing. It comes from the space full of air, from the intuition of the space full of air. So after all, these people are not doing deep philosophy. They are just formalizing simple intuitions about the world. In doing so, you can really read Newton in modern terms. He's just guessing correctly the existence of the gravitational field. So Newton, why he invented that? At the light of now that we've seen the general relativity is so right, so correct, so let's be general relativists. From the present knowledge, what has Newton done? He has understood, thanks to the inertial forces, that there should be a gravitational field. And he has written the gravitational field in its simplest way, which is this thing here. The distance between x and y being square root of delta ij xi minus yi xj minus yj. Okay, this delta, Einstein and Minkowski have given a better form to it, eta mu nu. This delta has become eta mu nu, just in talks with the space, and Einstein has gone to g mu nu, which is a gravitational field. It's like the Maxwell field. So the gravitational field is just this metric structure that goes there. When we go in quantum gravity, this becomes a quantum object. There is no container of the world. There is no empty space. There is no table on which things move. There is no canvas. There are just things moving one with respect to the other, one of which is the quanta of the gravitational field. So that was sort of all the introductory part, and this afternoon I'll start with some basic math, some review of basic SU2 representation theory, Peter-Weyl theorem, so that we can build the theory, the quantum theory then on the basis of that. See you this afternoon. And we'll have a tea before the class for whoever wants a tea. I have a few biscuits, but there are many biscuits. So maybe everybody gets half a biscuit or one biscuit. Okay, thank you.